Okay, we've had enough with adders. Time to go on to a different logic function. So the next thing that we'll talk about is comparators. This is where you're basically trying to compare. We have two data values, A and B, that are n bits long. And so we can do various different things to try and compare them to something. So two of the easiest, or not necessarily the easiest logically to think about is a 0 detector or a 1 detector. So this is a lot of times there's certain functions where it's useful to know, is the value that I have, all bits are zeros. So you take, instead of taking A and B and trying to compare them to each other, you take one of those values, either A or B, and say, is the value of A all bits equal to 0? So that's a 0 detector. Second useful comes in depending on what computations you're trying to do. It's also useful to know, is the value that I have all ones? So that's called a ones detector. So if every bit in that data value is equal to 1, then you output a single true or false value that says a 1 for all ones, or a 0 for no, there's not all ones. And same thing for 0 detector. A couple other things to do is comparison of A versus B. So one comparison that you could do is, I want to tell whether A is equal to B. So bitwise comparison, you look at all the bits and say, if every single bit of A is exactly equal to every single bit of B, then I say yes, these are equal to each other. And finally, a different type of comparator that you can do is a magnitude comparator. So I want to know whether A is greater than B or less than B, or something like that. So if A is less than the actual value of A is less than the value of B, then you return a true value. Here's a couple ways that we could do circuits that actually do either our ones detector or 0 detector. So for a ones detector, in effect, if you're trying to determine whether you have all ones, effectively that's an AND function. So here we've shown in the upper left, if we had an 8-bit ones detector, we're basically doing an 8-bit AND function. Now you could either create an 8-bit AND gate that's a single NAND function, but that would require 8 series transistors in a single stage, which typically is not a thing that you want to do in modern process designs due to just the amount of delay through 8 series transistors can get a little prohibitive and actually be worse than the design shown here, where in effect you can take a NAND gate followed by a NOR gate, which you can think of a NOR as effectively a not AND gate. So the NAND gate, the bubble of the NAND gate, and the not AND gate cancel each other out, and so you get an AND function out of that. So the not AND gate, due to De Morgan's theorem, is basically a NOR gate. So if you do NAND gate followed by NOR gate followed by NAND gate, you effectively get an AND function out of that. And you can, in effect, take this design and keep expanding it for, if you went from 8 inputs to 16, you could just place 2 of these next to each other, replace that final AND with a NOR gate again, and then followed by one last NAND gate. And so every time you double the number of input bits, you're just adding one more stage. It can be a fairly large layout, but it only grows by a square root of n, or a log n of the number of bits that you have, log base 2 of n. You can do a similar thing for the zeros detector. It's basically you do a not function at the beginning and then followed by a ones detector. So that could be a not and, which is basically a NOR, followed by a NAND. So if you had a 8-bit input there, you would have 4 NOR gates followed by 2 NAND gates followed by 1 final NOR gate to give us a zeros detector. So this is just one way to implement it, probably one of the most common ways. So for the equality comparator, the thing to keep in mind is we just want to compare each bit to each other. And the thing to keep in mind here is that if we use an XNOR function, so not an XOR, but an XNOR, in effect, each bit, if we, an XOR function says if both bits are 0 or both bits are 1, we get a 0 out, and if they're different, we get a 1 out. So in this case, if in XNOR, if both bits are 1 or both bits are 0, we get a 1 out. So it's an inverted from an XOR. So if basically if both bits are equal, we get a 1 out of an XNOR gate. So both bits are 0, both bits are 1, we get a 1 out. If all of the outputs of all of the XNORs are 1, then we get a 1 out of an AND function. So for an equality comparator, basically we want to do an XNOR of each A versus B bitwise to each other, and then follow it by an n-bit AND function. Now for a magnitude comparator, effectively, if we want to see if B is greater than A, then we can just compute the value of B minus A and look at the sign. If it's still positive, then we're basically B is greater than A. So one thing that we can note in when we're doing basically digital numbers, ones and zeros, and we have n bits, in order to calculate B minus A, we can note that that value is equal to B plus the inverse of each A bit. So if we take not A bitwise and add it to B and then add 1, we wind up with the same value as B minus A. And so we can take a normal adder and take B, do for each bit of A, we have an inverter that it goes through before it goes into the adder. And in order to do the plus 1, we just make sure that the carry bit going into, so the carry in of bit 0, we tie to 1. And then we can get B plus not A plus 1. And then we just look at the carry bit coming out, and that will tell us whether B is greater than A or not. As mentioned at the beginning of this week's topic, for ALUs, one of the other common functions is as doing a shift function. So I'll talk about there's a variety of different shifting activities that you can do. So the three main groups of types of shift that we can do is either a logical shift, an arithmetic shift, or a rotate. And so I'll go through the how that each of those functions here. So the logical shift shifts a number either to the left or the right. And so you need to say whether you're doing a logical shift right or a logical shift left. And after it shifts, since if we're shifting, let's say if we're shifting to the right, then every bit goes from its current value to one position to the right, so one position lower. And obviously on the very left-hand side, we're losing a bit on the left-hand side. So for a logical shift, what we do is we fill in that bit that we're losing with zeros. And so if we do a logical shift right of 1, 0, 1, 1, we fill the leftmost position with a 0, and we shift everything to the right, we'll lose our rightmost bit, and so we wind up with bits 3, 2, and 1 are now bits 2, 1, and 0, a 1, 0, and a 1, and the leftmost bit is a 0, and we've lost the previous bit 0, which was a 1. Now, when we do a logical shift left, again, everything will shift to the left. We'll lose the leftmost bit completely, and we fill the rightmost bit with a 0. So in this case, we're left with a 0, 1, 1, and then the new bit of 0 that got filled in. For an arithmetic shift, we do the same type of shifting, but the number that we fill in will be a little bit different than the logical shift. So we'll shift the number left or right. What happens when we shift right is we do a sign extension. So whatever the leftmost bit currently is, we'll keep that value there. So a 1, 0, 1, 1, when we shift to the right, we keep the leftmost bit value 1, and then we shift the bits to the right, we lose the rightmost bit. When we do a left shift, basically we fill it with 0 again. So an arithmetic shift left and a logical shift left look the same, and we get the bits 2, 1, and 0 shifting to the right, and we add a 0 in the new bit 0 position. Finally, when we do a rotate, we don't lose any bits. The number that would drop off on one side or the other rotates around and goes into the position that was vacated on the other side. So if we're doing a rotate right, all of our bits shift to the right. The 0th bit that's on the far right rotates around and goes now into the far left. So a 1, 0, 1, 1, the 1 that's on the far right drops off and shows up in now the far left, and so we wound up with a 1, 1, 0, 1. And finally, a rotate left of 1, 0, 1, 1. The leftmost bit will drop off and pop up in the right side. So when we rotate left, we'll wind up with 0, 1, 1, 1. So one type of shifter that can do all 6 types of shifts is what's called a funnel shifter. I'm going to describe this fairly quickly, and if you want to know more specific details about this, you can look in the book or do a search to get more details. It would take a long time to really explain it fully, and it can be a little bit of a difficult concept. But basically, funnel shifter, you take your n-bit number, which in this case shown in the diagram below is the number y, or the data value y, that has n bits in it, and you create a new value z that's 2n minus 1 bits long, and you have it inserted in z in a specific number of bits that's shifted from the right hand side of, so you don't have bit 0 going in bit 0, you have it shifted by a certain offset, and so you have an offset on the right of it, and then some additional bits that make up the rest of the 2n minus 1 total number of bits on the right hand side of your original value y, kind of in the middle, or not necessarily centered, but in the middle of the z larger number of bits. This just what we can do with this is we can shift by k number of bits, where k is greater than or equal to 0, but it has to be less than the total n value that we started with. And in order to use this, we're going to take the value of z and send it into n number of n to 1 multiplexers. So if we had a 4-bit number that we were trying to shift, we would need 4 to 1 multiplexers to get any value of shifting between greater than or equal to 0 and less than 4 shift. So I'll go into a little bit more detail in the next couple of foils, but again, this is a difficult concept and it would take a long time to explain fully, so I'm not going to spend that much time in this presentation going over it. You'll have to research more on the specifics in the book. So I mentioned on the previous foil that we had this funnel shifter that was a larger, we had to fill a data value of z with a larger number of bits than our original y data value. This chart here is meant to show what do we fill in the left hand. So we have the y value in there, then we have some extra bits on the left hand side of y and some extra bits on the right hand side, and the question is, what do we fill that with? This particular chart here is meant to show you what you would fill each individual value of the bits of z with. A little bit of a miss in the notation here. Instead of using y sub n, they're using a sub n, which is meant to say what values of the original data value, in this case a, where those values would go in the new value of z. Again, I'm not going to go into the full explanation here. Let's just say it's really complex. You have to fill in your z values carefully depending on whether you're doing a rotate right, arithmetic, or logical shift right, or a rotate right, or a rotate left, or in logical or arithmetic left. Depending on what type of shift you're doing or rotate, you have to fill those extra bits in with different values. So that's the main thing you need to know, is that filling in the extra bits is pretty complicated, and you have to know what to fill it with and have the right logic in place to do it depending on which function you're doing. This is showing one example of a way that you could generate a 4-bit funnel shifter using what's called an array functionality. So as I said, if you're using a funnel shifter, once you have the values of z and you know what type of shift you're doing and by how much, your value of k is how much, and left or right, and whether it's arithmetic or logical. After you know all of that, you need to do n number of n input multiplexers. So below is an example of using 4 to 1 multiplexers. So you can see below in the left hand side, they're using NMOS gates, a single NMOS gate, as basically a pass gate / mux type structure. One thing in this particular design, because they're only using NMOS gates, using NMOS to, if the z value that you're trying to send through to get your output y value is a 1 doesn't pass through as well through an NMOS device. And so you will get some VT drops in this particular case, and you would want to make sure to have an inverter or a buffer at the output of y3 through 0 in order to get a full rail swing after going through this multiplexer. So you can see each row of NMOS gates is basically performing a 4 to 1 mux function, because we have a select 0, 1, 2, and 3 going to each of the 4 NMOS gates. So only one of those selects is going to be high, which means only one of those NMOS gates is going to be on in each row. And it will be then selecting the Z value. So for the top row, we're either going to be selecting Z6, 5, 4, or 3 to go out on the Y3 output. And then the second row, we're going to be choosing either Z5, 4, 3, or 2 to be going out on Y2. And that all depends on which select is being chosen. So selects 1, 2, 3, and 4 are selecting 4-to-1 muxes, and then there's 4 rows of 4-to-1 muxes. So that's the N number of N input multiplexers. And then to the right hand side, it's just showing what the layout might look like for a single bit of this cross section of S, Z, and Y going to a single NMOS gate. On the previous slide, we went through an array funnel shifter, and while that might work okay or work pretty well for a 4-bit number that you're trying to shift, you can see how if we wound up going to, let's say, a 32 or 64-bit number, that gets pretty prohibitive. For example, a 32-bit number even, which is not quite as large as the modern microprocessors with 64 or 128 bits. A 32-bit number would require 32 muxes that are each 32-to-1 muxes. And that is something that generally in modern process technologies you probably wouldn't be able to actually do. It would just have too many problems doing a 32-to-1 mux, and doing 32 of them, it would take up a lot of area. So a solution to that is to use what's called a logarithmic funnel shifter. And this type of funnel shifter uses only log n number of stages of just 2-to-1 input muxes. And in addition to that, we don't actually need to decode the selects. So in the previous design, we had the select was K1 and 0, for example, and we had to decode those into S0, 1, 2, and 3 before we went into the rest of the function. In this one, you can see the way the hookup is being done. We have the same 0 through 6 that we were using before, but we hook up 2-to-1 mux to them in such a way where the connections go to the first 2-to-1 mux, and then we have a second 2-to-1 mux following it, and we have, instead of decoding, we just have an XOR function for the left shift happening, and then K1 and K0 controlling the select to each row of 2-to-1 muxes. And this allows us to do the shift. It might take a little bit longer going through 2 sets of 2-to-1 muxes, but the overall area of the layout that we're consuming, and again, this scales a lot better for larger shifters. So this in general is a little bit more the type of design we'd expect to see for larger bit values, going into 16-to-1 or 16 bits or 32 bits and above. In the previous foil, we went through a 4-bit logarithmic funnel shifter, and we showed how using 2 sets of 2-to-1 muxes, we could get a total shift of 0 to 3 bits. So we could do a shift 2 in the first set and a shift 1 or 2 or 0 or 2 through the second set. In this example, we'll be looking at how you might do a 32-bit logarithmic funnel shifter. In this case, what we're doing is we're doing 2 sets of muxes again, but the first set of muxes will be doing a shift by a multiple of 8. So we'll either do a shift 0 or a shift 8 or a shift 16 or a shift 24. And then the second set of multiplexers will be an 8-to-1 set of multiplexers where we'll shift by any value between 0 and 7. And so the total combination that we can get by shifting by a multiple of 8 up to 24, and then 0 to 7 individually after we shift by a multiple of 8, we can get any shift between 0 and 31 through our shifter. And the right hand side is showing how we might do the layout for this shifter. Keep in mind the total number of bits that we have for a 32-bit number that we want to shift is 2n minus 1. So we have our 32-bit number, and then we have an additional 31 bits that we have. It turns out that when you go in layout, rather than having those all in one row, it's better for the layout complexity and the wiring to actually line up those higher order bits in line with our lower order bits. And so we'll have bits 0 to 31 kind of in that top row, and then bits 32 through 62 are going to be lined up kind of vertically with our lower order bits. Then we can send those bits in the connections that we need by magnitudes of functions of 8 to the MUX4. The MUX4 is going to need 8 additional bits, because depending on whether we're rotating right or left, we're going to have an additional 8 bits going off to the side, one side or the other. And then when we do our final shift for the 8-to-1 MUX, shifting 0 through 7, then we'll wind up with a final 32-bit number coming out at the end. I encourage you, if you want to do some sort of logarithmic funnel shifter that's a higher order number of bits, study it more. This is, like I said before, it's a complex function and very complex layout, and so it would take a lot of time to try and explain it adequately in the lecture. So I'll leave it to the students to go read up on this more in the book or additional materials that you can find on the web. One other shifter that we're going to quickly cover here is what's called a barrel shifter. The barrel shifter is something that performs right rotations only, and it does that by using wraparound wires. For large shift values, those wires could be fairly long, but it works pretty well for shorter or not as long of a number of bits that we're trying to shift by. Now, the thing to keep in mind is, if you're only doing right rotations, what if you want to do a left rotation? It turns out, if you look at the way left rotation work, a left rotation can be done by noting that it's a right rotation by a number of bits that's n minus k, where k is our value of number of bits that we're rotating. And it's also worth noting that shifting or rotating right by n minus k is also equal to the inverse of k plus 1 bits. So if we rotate right by inverting k plus 1 additional bit to the right, it's equivalent to rotating left by k. And then additionally, doing a shift is actually like doing a rotation by masking off the end bits by the appropriate value, either a 0 or 1. So let's look at how we might do that in the next slide. So here we can see a barrel shifter with three kind of enhancements to it. So in the upper left-hand corner, this is showing a 4-bit barrel shifter which only does the right shift. So if you're doing a shift to the right, you just can use that design for your 4-bit barrel shifter. Right below that is showing how we can do a left or right shift. So if you remember, I said if we want to shift left, we can do that by shifting right by inverting K and then shifting 1 plus the inverse of K to the right. So here what we do is we have a value. If we're doing a left shift, we first do a pre-shift of 1. So the top row there is, if left is coming in, it has a value of 1, we pre-shift 1 to the right. And then we follow it by, if left is a 1, we send K through an XOR, which effectively, with left being a 1, will wind up inverting the values of K, and then we'll do an inverted K shift to the right. And so in effect, by doing the pre-shift of 1 and then inverting K and shifting by that to the right, that's the equivalent value will come out as if we had done a left shift by K. So that's showing how to do a left and a right shift with this pre-shift and then the XORs of the K value by the left value. And then finally, on the right-hand side, we have the left-right shift functionality in the top, and then we have an additional functionality for doing our mask bits and sign bits, and I'm not going to go into the details of what the combinational logic is in there, but that will allow you to do the equivalent of a shift as opposed to a rotate. And so depending on how much you're trying to right shift or left shift or rotate, we're going to get the appropriate values masked off, and or the value just passed through if we're just doing a right shift or left shift. Now, similar to how when we were talking about the funnel shifter, when we were talking small number of bits, like the 4-bit funnel shifter, we had 2 sets of 2-to-1 muxes. And then when we went to the logarithmic, we had a higher order size of mux that we were using. So here we can see, using the barrel shifter, if we do a 32-bit logarithmic barrel, instead of doing 2 sets of 2-to-1 muxes, we can now do a 5-to-1 mux followed by an 8-to-1 mux. And in this case, the 5-to-1 multiplexer can either rotate by 0, 1, 2, 3, or 4 bits. This will handle a potential pre-rotate by 1 bit, followed by a fine rotate of up to 3 bits. So we could either do a rotate of 0 or 1, depending on if we're doing the pre-rotate, and then we can rotate by an additional 0, 1, 2, or 3 bits by doing that 5-to-1 mux at the beginning. And then when we're doing our 8-to-1 multiplexer, that's going to do rotating by functions of, or multiples of 4 bits. So the 8-to-1 multiplexer will allow us to do either a rotate of 0, 4, 8, 12, 16, 20, 24, or 28 bits for the more, the larger, rotating by larger jumps of data. And so the second 8-to-1 mux will allow us to rotate up to 28 bits, and the first one allowed us to rotate up to 3 bits, which gives us up to 31 bits worth of total rotation. And then we can choose whether it's a left or right rotation based on the logic that we talked about on the previous foil. And then finally, the masking bits on the bottom will handle whether it's a rotate or a shift, depending on, and determine the number of bits that come out. Again, I'm not going to go into the details of exactly what each of those stages looks like. If you're designing one of these, you really need to understand it. It's going to take a lot more time to understand this than just quick 5 minutes on a couple foils here. So you'd have to study it in a lot more detail for this specific type of shifter or rotator that you want to use.